Okay, thank you very much. So we just continue where we stopped yesterday. So diameter of this graph, or in general, diameter of a Cayley graph. How will we check it? So diameter of this graph is 3, because each element of the group can be expressed as a product of at most 3 generators. And now it might be unclear why, and since I'm unsure if it's clear why, therefore it's better to have first some simple example. So, and again, let's just choose example which we already introduced, because maybe then it will be even easier since you already remember the example. So we have here Q3. So let's have it back. You probably have it, maybe you did write it in your notebooks. So if we have this graph, and we are wondering what the diameter is. So this is the graph for the group gamma. I'm always using for group gamma because I'm using G for graph. So we are kind of unlucky that group and graph start with G, and degree and diameter start with D. So anyway, group will be gamma, and we are using the 2, so the direct product of 3 groups of 2, and we use generating set to be, I'll take it with shortcuts, so we will just like without using brackets and Tomas. So 0, 0, 1, 0, 1, 0, and 1, 0, 0. Okay, so these are our generators, and our vertices are 0, 0, 0, up to 1, 1. Okay, and now we want to know what is the diameter of this graph. Well, do you have some guess? 3, because from this vertex, how many vertices are the furthest from this vertex? This one is of distance. What is the distance between this one and this one? 3. Is there any other vertex which is of distance 3 from this vertex? No, everything is 1 or 2, right? There are 2 vertices of distance, 3 vertices of distance 1, then there are a few of distance 2, and 1 of distance 3. Now, how would we show it similarly as there using groups? The diameter is 3 of this graph because every element can be expressed as at most 3 generators. So if you take that element 1, 1, 1, it can be written, well, here, since we are using additive group, we are using plus as operation. So here, the group operation is plus. So if you take generator 0, 0, 1 plus 0, 1, 0 plus 1, 0, 0. Let me put the commas so we are not getting a bit confused. You will get this element. Okay? It means from this element get to this element, it takes you 3 steps. 1 step, 2nd step, 3rd step. Okay? How many steps would we get to this element? It will be only 2 steps because you would get there as 1, 0, 0 plus 0, 1. Right? 2 steps to get this vertex, 3 steps to get this vertex. Let's say if this one is 0, 0, 1. We know that it takes only 1 step. So if you want to get to 0, 0, 1, well, this one is already a generator. So you just take that 1 step. Okay, since I'm not very sure you understand it, I will give you one more example. So now try it by yourself. Let's have a group Z 9 and generating set X, which will contain let's make it a little bit simpler. So if there is 1, it's a little bit clearer. 1 and 3. So if we are putting 1 and 3 to our generating set, just so the generating set is defined properly, we must include also inverses. So what are the inverses for 1 and 3? 6 and 8. Okay, so these are the inverses. So write the graph for Z9 and edges. So it will be easy. You will have 9 vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's do the notation. 0, 1, 2, 3, 4, 5, 6, 7, 8. And edges. So jumping by 1 and jumping by 3. So jumping by 1 and jumping by 3. Okay. And now the diameter. So we can pick any element. Just let's pick just 0. Okay, so this is the advantage of a Cayley graph. If you study distances from one vertex to all the other, the same will apply for all the other vertices. So if you want to know the diameter, fantastic. You just need to check the distances from one vertex. So what do you think is the diameter of this graph? Okay, so which vertex is of distance 3 from 0? Is there any vertex which is of distance 3? It looks like no, it looks like the diameter is 2. So let's just double check it. But so what are our generators? 1, 3, 6, 8. So we need to express every element as a product of at most whatever. If the diameter is 2, of at most 2 elements. 0, 1, 2, 3, 4, 5, 6, 7, 8 equals in terms of generators. Actually, we can even say every non-identity element because 0 we don't really have to express in terms of generators. However, we can, let's say 3 plus 3 minus 3, but it's not necessary because we are already there. So the distance between 0 and 0 is just here. So actually, we don't have to express the identity element and the next ones. 1, great. 1 is the generator. 3 is a generator. 6, 8 is a generator. So those can be expressed just as one element from the generating set, and 2 will be, well, we can use many possibilities. It can be 1 plus 1, but it can be also 3. No, actually 3 minus 1 will not get. I don't think there is other way. 3 and 8, but we will get 2. Oh, sorry, yes. 1 is covered. Sorry, yes. So we can also use 3 plus 8. Okay. Great. Now 4 will be, for example, 3 plus 1. 5 will be 6 plus 8, I guess. 6 plus 8 is 14. Modulo 9 is 5. And 7 will be 8 plus 8. 8 plus 8. 8 plus 8 is 16. Modulo 9 is 7. So as you can see, every element, every non-identity element can be expressed as sum. We are saying now sum of the product because we are using additive group as at most 2 elements. Look, this one is expressed 2 elements, 2 elements, 2 elements, 2 elements, and this one is 1 element. Therefore, the diameter of the graph is 2. Now, very similarly, just with much more complicated generators, is applied here. Here we want to show that the diameter of this particular graph is 3. So every element must be expressed as a product of at most 3 generators. So what is this group which we are using? It's not mentioned here, so let me put it a bit back. So the group which we are using is mentioned here. It's H times H times H, and in the last one, we combine it with the Z12. So remember it, cyclic group is 12 elements, and here we have H, H, H. And now I want to express every element. So how am I doing it? First, I am focusing on first 3 coordinates being anything. So I'm doing it in general way. Here, I was expressing only one element. But well, in this one, m is general number. So I mean, it's not possible to do it one by one. So I must just cover a set in one step. So here I'm covering how many elements. Since here I have m possibilities, here I'm covering m to the power 3 elements to be expressed in a bit general way. And again, here I'm taking x1 to be anything, x2 to be anything, and x3 to be anything, and this last coordinate to be 1. And since I'm studying it for the group Z12, I need to cover the first coordinate, the last coordinate to be 0, last entry to be 1, 2, up to 11. And if I show that all those elements can be written as a product of 3 generators, then I know that the diameter of my Cayley graph is 3. Well, as you can see, I'm using here some kind of a multiplication of some elements and inverses. The reason for that is I want this to look beautiful. I could choose this the other way around. I could just shoot here, I could do it similarly as in this one, because this one by chance it's it looks very nice. I could do it nice way here, but then this one would be some kind of combination. But I want this one to be very nice. So, well, since I know that my generator is having anything in the first place, then even this one is anything. So it's fine, right? Even this one is anything from the group, because I am covering all elements in that coordinate. Anyway, how can I express x1, x2, x3, 0? Well, just as multiplication of 3 generators of the form B something. Because if I take here x1 identity, identity A, multiply with x3 identity for the group H. This is identity for the group H. Let me just again maybe put it back. So we exactly know, look, is identity element of that one group H. So identity here is A, E, right? So great. And now what is our operation? Maybe we also forgot from yesterday the operation. So the operation, which is mentioned here, but we studied it quite in detail last time, so you maybe remember. The operation means that we are shifting, the automorphism is shifting the coordinates, right? So if we are shifting the coordinates by this one, so this is telling us how many moves do we have to make in these coordinates. So this 8 means we are moving this x3 8 times. Well, since we have only 3 coordinates, 8 times or 2 times is the same. So because if we move it by 3 coordinates, it will come to the same place. If we move it by 6, it will again come to the same place. So actually, we just move it not by 8, but by 2. So this one, by using again this product which we described yesterday, will be moving this element by 2. So this 8 says that this x3 will be jumping to this place. So if you put first and second together, where will we stand after the first step? It will be, so multiplication of this one and this one will bring us to x1, or let's just put it together, x1 times E x1 times E. Here will be E times E, and here will be E times, and x3 will jump there. E times x3, and the last one will be 8 plus 8, which is 16, and 16 modulo 12 is 4. Since the product is maybe slightly complicated, maybe we forgot what was discussed yesterday, because I can hear quite some noise happening here and there. So let me just remind you how it works, because I don't want you to get a little bit lost. So when we have element x1, x2, x3, and some number, let's say 2, and here we have x1 prime, x2 prime, x3 prime, and here we will have, let's say, 11. So what will be the result of this one? The result of this one will be, the last one is easy. The last one is easy. You just make this one plus this one, right? Y plus Y prime. So in this case, it will be 13, but since we are modulo 12, it will be 1. Okay? And what about the first 3 coordinates? Well, these ones are fine. They are staying where they are. x1, x2, x3. And these ones are moved by 2, because this number is telling us what is happening in these 3 coordinates. So x3 prime is moved by 2. It's not coming here, it's coming here. And x1 is jumping here prime, and x2 prime. So this is the road. Now it's just identity. So it will be just x1 times identity will be just x1. Identity times identity will be just identity. Identity times x3 will be just x3. So this is the result of the product of those first 2. Now we need to still multiply it with the third one. But if you now multiply it with the third one, now this element will be moved by 4. Because now we are standing here with 4. So it will be moved by 4 steps, which is the same as moving it by 1 step. So x2 will jump here. Again, those identities just will keep us having the same coordinates. So just x1 will stay x1, x3 will stay x3, and this x2 will be moved by 1. And in the last coordinate, we will have 4 plus 8, which will be 12, and 12 is 0. Done. So here, when we have, let's say, expressing 1, 2, or other elements, then it's slightly just more trickier. So again, I have to choose here x1 times x times inverse of x3, because I need to use the inverse to give me finally my x3 here. Let's see why. So again, if I multiply this one and this one, obviously in the last place I'm going to get 9. That 9 is still important, because that 9 will play a role what is happening here. So let me just these 2 elements, let me multiply them, and then let me just write it here what it is equal. So now we know that the last coordinate is 9, because 8 plus 1 is 9. Okay, this one is not going anywhere. So here, this one stays as it is. x1, x3 to the power minus 1. And let's see, since it is 8, these 2 elements, well, now why am I using here 2 elements? Well, because in order for me to express this element, I was using only generators B. That was quite simple. And what is B? It's written my generator B is mentioned there. We are working on the first coordinate, and the last one is always A. But here we are using B, we are using A, and we are also using this kind of elements which are actually inverses to these elements, right? We know that the set of these elements are inverses to the set of these elements. But that's fine, because they are our generators still. Same as when were having the previous graph, which I gave you example, which had generating set 1, 3, 6, 8. As you can see, also 6 and 8 are our generators. Also 6 and 8 must be used because they also give us edges, right? The other way around. So these are same useful generators for us as these generators. Great. They are also bringing us by edges somewhere in the graph. Anyway, x1, x2, x3, 1, we are using these 3 types of generators. So what is this type of generators? This type of generator, we are working on the first coordinate, and the last one must be 8. Second type of generator is we are working on the first 2 coordinates, GG or anything. And my anything, I just choose x3, x3. Because why? Because I know that at the end, I just need to get this one x3 here, and the other x3 will cause some small complication somewhere else, but I will sort it out by this one. And the last generator, I'm working on the second one, and last one must be 4. I'm working on this one, and last one must be 4. But I knew, fantastic, these 2 will not influence me in the second position. I'm safe there, so I can just keep it x2. I don't have to multiply with some other number, some other element to the power of some -1 or whatever. As you can see here, for example, I had to work a lot because I have to sort out complications which were caused in the previous steps. Anyway, let's just multiply these 2 elements, as I mentioned. We already mentioned the first one. Moving this by 8 will bring us actually move by 2. So these 2 elements first will move here and then here. So you will actually get x3 still coming here. Here will be like E, and here will be x3. So this is the result of this multiplied by this first 2 elements. And you have here x3 to the -1, so inverse to x3. So this one will cancel. So we are standing x1, identity x 9. And since there is 9, it means shifting this 9 times means it will stay where it is. So the last step will be easy. Just multiplying this one with this one, and this will be our result. Next one. We will still maybe discuss this one and all the other ones which are mentioned in the next page. We are just doing it the same way. So I think once I show you one more, I think you would be able to understand all of it. So again, we want to express set of m to the power 3 elements because here we have n possibilities, n possibilities, n possibilities. And this set of m to the power 3 elements can be expressed as 3 elements which we are multiplying and which they have this form. So again, first one we are taking from the set. This one, so we are working on the first and third coordinate. As you can see, x1 is here, but the last one must be -1. The other A's have working on first and third, and last one must be 4. So it looks like there might be a typo there, or not. No, it's I don't think it's fine. Oh, it's fine. Sure. Yes, we are working on these A's. So yes, we have -1, -1. In the last one, we are working on the B, which is there, which is 4, which is 4. Okay, so now we are multiplying these 3 elements. And again, what will be the result? Well, we now must shift by -1 or by 11. So if I'm writing here -1, it's the same as writing there 11. I just write a -1, or here I'm just writing -1 because I just thought it's easier because you just can shift it by 1 back, then going 11 times forward. So this one, we know that we are shifting these coordinates. These coordinates will stay the same. So let's just write the product of these ones. So it will be x1 e x1 -1, x1 e x1 -1. But now, what is going to happen with these coordinates? Well, -1 and -1 will give us -2 or 10. So -2 or 10. Doesn't matter. Let's just put 10 there. And this will be shifted by 1. Okay? So this one will come here and this one will come here. So it will be EX to X2. EX to X2. X2. So E is just identity times some element is just that element. So E here can be omitted. We don't need to write them down. So it will be X1, X2, and here last coordinate X1, X2, and 10. 10 means, or 10 or minus 2 means we are moving these coordinates by 10 or by minus 2, which means they are actually moving by 1. So this will jump to the third place. And in the first and second place, there will be just E's. So first and second place will not be influenced. And in the third place, we are, so since this will jump to the third coordinate, then we will have there not only X1, X2, but we will have the X1, X2, X to the power minus 1, X1 to the power minus 1, and X2, because this will be added. And beautifully, this will go out because it's element that is inverse, element that is inverse, out. So we will stay there only with X3 as we want, right? And then we nicely show that every element of this form can be expressed in this. Again, instead of doing it this way, I could just put here similarly just here X1, X2, X3 somehow, but then I would have a mess here. And I would have to show that this mess, what would be here, really is expressing all elements of the type anything, 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 and 2. And in the next page, there are a few others which are expressed, but it's very similar. So I think we don't have to discuss the others. I was told I don't have to continue 7, 8, 9 up to 11. So just probably we'll have these presentations soon. So you can look at it and you can see if you understand. And next week I'm still here. So in case you have some questions, you can ask if something is unclear. Okay. So I presented here this construction of large Cayley graphs, and it's a little bit maybe unclear, like how did I come with this construction? How do we construct these Cayley graphs? Why did I choose this generating set? Why did I choose this group? Like it's all these questions are unclear. Obviously, it is a challenge to come with something which is going to produce large graphs, but there are some techniques, there are some strategies which are known to work for construction of large graphs. And one of these strategies is called graph lifting, lift of graphs. So here it is described what is graph lifting. So let me again go step by step and explain to you how do we use lifts of graphs to construct from very small graph some large graph. So we will start with a graph with 2 vertices. So you will have 2 vertices. Those 2 vertices will be not only connected by an edge, but both of them will have loops. But the resulting graph obviously doesn't have loops because we are in our main graph, in our graph which is special for given degree and diameter, which is very large. Obviously, we don't use loops and multiple edges and stuff like that, but we are using loop in the original graph for the construction of large graph without loops. So we have 2 vertices, we have 1 edge between them, and we have a loop. So there will be an example of our graph. As you can see, we are taking G to be undirected graph. This is our example of a graph G, which is undirected graph. But the next step, we are considering all the capital DG. So DG will be set of all directed edges. So we are thinking about this edge as 2 oppositely directed edges. So as edge going directed edge going this direction, and also directed edge going this direction. And also similarly for every edge. So even we are thinking about this loop as being combination of one loop going this direction and one loop going the other direction. And similarly. Okay. So it is undirected graph for us, but for a while to construct the leaf, we are just assigning some elements of the group to the set of directed edges. Okay, and undirected graph set of directed edges. Now A will be any finite group which we choose. Let me just again choose something simple as a first example, just a cyclic group Z5. So my A will be a cyclic group Z5, cyclic group with 5 elements. And now we are going to construct a leaf with the help of this assignment. We will assign elements from the group to those directed edges. So directed edges will be having some element from the group. So again, you would have to just choose the element depending what you want. So let me just choose something, and later I can explain you why we are choosing such elements, or how can we construct large graphs and what must be our choice. So anyway, let me choose 0, here 1, and here 2. But again, for it to be defined properly, to the edges going the other direction, you must have the inverse element assigned there. So the edge going the other direction must be having inverse element. Since we are assigning 1 to the directed edge going this way, it must be 4 assigned to the opposite direction. Since there is 2 assigned to the edge going one direction, it must be 3 assigned to the edge going the other direction. And now we are going to have now large graph. So from the graph which has only 2 vertices, the lift will have 2 vertices, but for each of those vertices, we will have actually 5 vertices, because the group which has 5 elements, let's say if this one is U, it will bring us to U0 up to U4. It will bring us to U0, U1, U3. Because for each element, we will have 5. And similarly with V, we had 1 V. Now we will have 5 V's. V0, V1, V2, and V4. Maybe just let me also tell you, in case we would apply this strategy, this lifting method to directed graphs, obviously we wouldn't have this condition. We wouldn't have to consider that the oppositely directed edges would have to have the inverse element. So since we are undirected, it's let's say slightly there are some more conditions mentioned, but you could also use this graph lifting for directed graphs. Then you wouldn't have to worry about having the other directions for the edges which I mentioned here. These other directions and inverse elements are just mentioned to define the concept of. And now if E is a directed edge going from U to B in that graph, and B is the voltage assigned, so voltage just means element of the group. So that group has 5 elements. So each of them for us is called voltage. So we have 5 possible elements which we can assign those voltages, and they are bringing us edges. So if we have U to B, U going to B, and having there 0, it means we are going from UA to VAB. But again, between A and B, in general, if we are not specifying what group operation we are using, we are just putting AB. But in general, as I mentioned also previously, it means VA, group operation, and B. So, well, so it's whatever is the group operation will be between A and B. Since this is additive group, we are using actually not VA times B, but VA plus B, where B is this number assigned. So in this case, it will be just UA is connected to VA. However, we also have HU connected to HU, HU connected to HU, and having 1 there, which means in the lift, so this is in graph G, it means in the lift G alpha, we will have UA to UA group operation, which in our case is plus 1. And similarly, PA will be connected to VA. Since we have here, let's say 2, doesn't matter if we are considering 2 or 3, because since we are undirected, 2 or 3 will bring us to the same graph. 1 or 4 will bring us to the same graph. 2 VA plus. And now, how does it do? So as I mentioned, since there is 0, U0 connected with V0. First, it should be directed, but at the end, since we are studying undirected graphs, we will just suppress direction. We will just omit directions, and it will be just U1 going to V1, U2 going to V2, and so on. And here, UA connected to UA plus 1, so we just jump by 1. Plus 1, plus 1, plus 1, plus 1, plus. Again, if it would be directed, we would just write direction. If it's undirected, doesn't matter if we are using this element or this element to construct it. Both elements will just bring you to the same. Similarly here, now we are jumping by. This graph which I constructed, what graph it is? Peterson. So see, again, just different possibility to draw a Peterson. And now, how did I construct the construction which I mentioned previously, that graph? I actually did construct it with the help of graph lifting. And the graph which I used as my basic graph was also quite simple. It had 3 vertices. It was quite some time ago, so maybe let me just give you a hint, and you will just, maybe it will be your homework to check if it's defined correctly, and tomorrow I'll double check it and I will finalize. So now we have M edges between, let's say, let's have vertices U, B, and W. And we will have M edges in between. Just to make it simpler, let's just use, okay, I'm wrong. It was not 3 vertices, it was the other construction, which I didn't mention in my lecture. Now we must have a graph. Okay, let me first mention this one. So if we would want to construct the graph with 3m to the power 3 vertices, we would use 3 vertices here and m edges here and m edges here. So here is m edges, here m edges, and similarly here m edges. And there will be also loops, which will be most likely around m-half loops. But this was leading to a graph having 3m to the power 3 vertices. But the construction which actually I presented is not using 3 vertices, but 12 vertices, and going somehow similar. So now the construction actually I presented, this one would give us 3m to the power 3, but the one which I wanted to show you must give us 12m to the power 3, because you remember I was using group set 12. So I had 12 vertices in my 1, 2, 3, 4, 5, 6, 7, 8, 9, then 11, 12. I had 12 vertices in my graph G, and my leaf G to the power alpha gave me 12m to the power 3 because of the leaf. So here I had vertices 0, 1 up to 11. And connection was kind of related to those generators where I was jumping by 1 or by 4. So I think it was connected this way. And here jumping by 4. 1, 2, 3, 4. And so on. One, two, three, four. 1, 2, 3, 4. And one more. Okay, so we have this graph, and let me just check if, because if the diameter of the big graph was 3, I think it will work. You must kind of get from every vertex to every vertex by 3 steps, which will probably work. But except for this, you must have this property satisfied. No, the property is mentioned only in the next page. Yes, please.
So A is H cube.
Again, repeat your question.
The group A, in this case, is H cube.
Yes, correct. Or just to simplify, let's slightly specify the group. So in general, yes, it's H cube, but we can also use just Zm times Zm times Zm for the to illustrate it in a simpler way with the voltages assigned there. But yes, in general, it's just a group having m to the power 3 elements, which is H cube. Good. And now, okay, now I don't remember how were the voltage is assigned, but the property which is important is, okay, here we have one more graph, which is a lift of certain graph, but this is the important part which I want to mention. But before I mention, let me still tell you about this example. So as you can see, this example is very similar to the example of Petersen graph, which was just here used as a lift. Since we are assigning element 1 to the HD, it means NCR, since we are assigning voltages from cyclic group with 6 elements, Z6, it means instead of having one vertex, this graph is just graph having one vertex. We are going to have 6 vertices. One vertex using group with 6 elements will give us 6 vertices. Generator 1 will give us edges from U, let's say UI to UI plus 1. Generator U2 would give us edges UI to UI plus 2. Again, if you would be taking inverses, since our graph is finally undirected, it doesn't matter if you are choosing 1 or 5, or it doesn't matter if you are choosing 2 or 4. So it will bring us to the same graph. Now, what I wanted to mention about the diameter of the length of this graph, because we are not caring about the diameter of this graph, we are caring about the diameter of the huge graph, not having 12 vertices, but having 12 m to the power 3 vertices. And the diameter follows from this property. So, again, alpha voltage assignment in a graph, a group, that one, no. Then diameter of the big graph, not of the small graph, not of this graph, of the big one. So, not of this graph, of the lift of this graph. The diameter of the big graph will be at most k, even only for each ordered pair of vertices. And for each ordered pair of vertices of the small graph. So let me just pick a pair. So for example, let me pick this one and this one. but you must pick each pair, and it must work for each pair. So for each pair of vertices, there exists a walk. So since I want to show that the diameter of this graph will be 3, a walk of like at most 3 of voltage G. It must work for every two elements for every voltage. So you must be able to do this from this element to this element by 3 steps for every voltage. So voltages on these edges must be assigned in such way that I think the way how it was, let's say here it was M edges, and there were something like, in case I'll be simplifying it and using just the direct product cyclic groups, it would be just here I would be using 0 or 1 0 0, 2 0 0, up to actually up to M minus 1 0 0, and so on. And I would assign some voltages there. Since I did this construction a few years ago, I actually didn't plan to introduce this voltage assignment. I just got this idea that it will be easier for you to understand how I constructed the graph. So the construction was anyway done in this way: small graph using lifts and using this property to get my diameter from every element to every element. I had to get by any combination of I, J, K, where I is from this group, J is from this group, K is from this group. So it's not only having one path of length 3 or one walk of length 3, it's having one walk of length 3 for every element of the group. So I mean, there will be many edges, and we must come there using any element, using this property. Okay, we are done with the lifts. We are coming to the next part, in case there is time. There is time. So the next part is the degree diameter problem now for specific Cayley graphs, not general Cayley graphs, but for Cayley graphs which are coming from abelian or cyclic groups. So similarly defined problem. So the advantage of this research problem is that it's studied for many directions. Somebody studied it from vertex-transitive graph, some researchers for Cayley graph, and those which like groups more even going to Cayley graphs of abelian groups, which is commutative groups or cyclic groups. So again, we can define the same degree diameter for specific groups. So again, the problem will be find the largest possible graph for given degree and diameter, but now for abelian Cayley graphs, which means Cayley graph of abelian groups, or for cyclic Cayley graphs, which means Cayley graphs of cyclic groups. And actually, there will be quite some limitations because group being commutative means that you are not going to be able to construct such large graphs as you will be using general groups. Why? Well, because it's quite a disadvantage to have that commutativity. Because let me just give you an example. So, in case we are constructing a Cayley graph using commutative, then let's say we have some element U, and let's have two generators, A and B. Well, the generator, let's say if it's a cyclic group, let's say Z whatever, Zn, that U, let's say Ui or just I, will bring us to I plus A and I plus B. Because just one particular vertex. We are just focusing on one vertex. It will be connected to these two vertices. One, I plus A and Y plus B. But then this one, I plus A, will be connected to I plus A plus B. Because B is also generated. Plus A plus B. But this I plus B will be also connected to I plus A plus B. So if the group is, and even worse, if you have generator C, I would be connected somewhere to I plus C. But again, you will get some kind of the same structure. Here somewhere would be I plus A plus C. And finally, and here, let's say we have here also another one, which would be AB, AC, BC. I plus B plus C. And I plus B plus A plus B plus C would be one element, right? Which, and what I wanted actually to say, I plus A plus B plus C, in case we are studying commutative groups, would be exactly the same as I plus A plus C plus B, right? Would be the same as I plus B plus A plus C, and so on. So there will be 6 of them. I plus C plus B plus A, which means where A, B, C can be anything. It can be, this one can be 3, this one can be 5, and this one can be 8. Let's say, and Zn can be Z 50. Okay? So from the element, which is, let's say, 7, 7 plus 3 plus 5 plus 8, 16 plus 7, I think 23. So any combination, any order of A, B, and C after 3 steps would bring you only to one vertex using those 3 generators, which is a huge disadvantage compared to general Cayley graphs. Because in case you are using general Cayley graphs, let's say those semi-direct products which we mentioned before, from one vertex using 3 generators, you can come to 6 different vertices. Because all these can be different elements in a group, which means different vertices. But being abelian, it's going to be always going past to one vertex. Therefore, the upper bound for general Cayley graphs was about d to the power k. So the largest number of vertices, the theoretical bound, which we are still very far from constructing something close to the bound. So the theoretical bound for CDK, largest possible Cayley graph of given degree and diameter, is about d to the power k. That was the bound which we had here, 1 plus d times d minus 1 plus and so on. So that bound, Moore bound, is about d to the power k. And you can see when we are studying Cayley graphs or abelian Cayley graphs, suddenly it's d to the power k divided by k factorial. So much less. Okay, so now again some result, which is for cyclic Cayley graphs first. But again, since we are okay, we can still start a little bit, even if we are 5 minutes before the end of the lecture. Because yesterday, I think maybe the next speaker had to start a bit late because I was too slow. So let me just start what we are going to do tomorrow. So we will have a construction now of cyclic Cayley graphs, which will be coming from finite fields. So it will be constructed with a group which is using additive group of a finite field, multiplicative group of a finite field, and a cyclic group with 13 vertices. Again, 13 is because when I'm looking for the construction, I am trying to, because you might be wondering why now Z13 and previously it was Z12. Well, I'm trying to optimize the parameters which I have. So let's say here, when I was using 12 vertices in my graph, which I was lifting, I was thinking, well, what is better for me? 12 vertices and having more generators, because more generators is bad. More generator means bigger degree. I want to push degree down and I want to push number of vertices up. But if I'm having, let's say, 12 vertices, I need to have more generators. Let's say if I was having the other construction, which I was first trying to show you, 3 vertices and lifting such graphs, then if I am lifting this graph, then I can have smaller degree. I can have just not that many loops, not that many edges in between, and then I'm comparing. I'm lifting this one, I'm getting 3m to the power 3 vertices in my lift. Here I'm getting 12m to the power 3. But this is not necessarily going to give me a better result than this one, because maybe the edges which I must add here will increase the degree so much that at the end I need to express my m in terms of d. So I don't care that 12 is so much bigger, because what is my m in terms of degree? How will be looking my final bound in terms of degree? So those are the challenges. So in general, let's say if I was using this type of graphs, I was studying, okay, maybe I don't know yet what will be the order of my group. Let's say it will be Pm to the power 3. And how will be my degree expressed in terms of m? And then I will see what will actually work the best. Great. We are done for today. We will continue tomorrow. Thank you.